Hi folks, welcome to MEAM 543, Performance and Design of UAVs. I thought it'd be useful to start by parsing out the words in the title of the class. A vehicle is used to transport something from one place to another. In the aerospace business, the thing that's being transported is usually called the payload. And like all things in aerospace, we pay a lot of attention to the weight of the payload. The other two main categories of weight on an aircraft are the empty weight and the energy weight, which consists of either fuel or batteries. The empty weight is mostly structural weight. Okay, so the stuff we might be transporting, it could be weapons, it could be sensors, it could be communications equipment, could be supplies or packages, for example, in the Amazon Prime Air project. And all that stuff together is payload. And then the other measure of the productivity of the vehicle is how far are we able to move the payload. So we take the weight of the payload times the distance we're able to move it. That has units of energy, and that's a measure of how productive our vehicle is. Okay, of course, we're not interested in just any vehicles. We're interested in vehicles that operate in the air. And one of the signature features of an aerial vehicle is that it doesn't get to resist the force of gravity with no design intent and with no power. If you look at a ground vehicle like a train, it can resist the force of gravity just by sitting there. You don't have to design it in any special way, and you don't have to exert any power. But an aerial vehicle has to do something special. It has to generate lift, and lift requires power to stay airborne. So that's the main distinction. We also need design intent to make an object stay airborne. Okay, there are four major categories of aerial vehicles. There are blimps or dirigibles, which are buoyant vehicles. There are rockets, which stay in the air by virtue of expelling mass out the backside. But we'll spend most of our time on the two categories in the center here, the fixed wing and the rotary wing aircraft, which share a common feature that they resist the force of gravity by deflecting a mass of moving air in a downward direction. So they create downward momentum in the air to generate lift. Another distinguishing feature of aerial vehicles is that we're not always concerned with range as the metric of mission performance. Remember, range is how far a vehicle can carry its payload, and that's the same whether it's a ground vehicle or an air vehicle. But some air vehicle missions don't require us to actually transport the payload. We just need to lift it in the air and hold it there. A typical example would be an observation or surveillance mission, in which case we might only be concerned with how long the vehicle can hold the payload in the air, something that we call the endurance of the vehicle, another important performance metric. We're going to be thinking about aerial vehicles which don't have a crew. And the primary consequence of this, from our point of view in the semester, will be that we don't have to account for the weight and the safety systems that are normally associated with having people on board the airplane. We want to be clear here that we're considering both remotely piloted vehicles, where there's still an operator, just not aboard the vehicle, as well as totally autonomous vehicles, where the navigation and decision-making processes are on board the aircraft. For our purposes here, it won't matter whether the vehicle is remotely piloted or totally autonomous. I want to spend just a few moments here talking about a distinction between navigation and control, which is important for any student of robotics to understand. Navigation is an outer loop process, really a kinematic process, where we know where we'd like to be, and we know where the actual aircraft is, and we come up with a plan for navigating from one point to another. Notice we don't have to write F equals ma. There's no forces involved in navigation. It's only kinematics. On the other hand, once we know how fast we'd like the vehicle to go and in what direction we'd like to point it, we have to invoke physics, and that happens in an inner loop. That's where we have the control loop. So the inner loop control happens at the level of F equals ma, and that's what we'll be doing in this course. We won't be doing the outer kinematic loop, where we do path planning and navigation, which is a higher level function. If you want to learn about that, you should take MEAM 620. More of the details of control happen in MEAM 513, but we'll get an introduction in this class. We've used the word performance a number of times already. In the airplane business, the word performance has a pretty standard meaning. If you look at a textbook, there are lots of textbooks that have aircraft performance in the title. You look at a textbook like John Anderson's Aircraft Performance and Design book, he's got a couple of chapters on airplane performance. It has this pretty standard set of things like thrust and power required as a function of speed. You might also look at how it varies with altitude. You'd have takeoff and landing distances and maneuverability. How quickly and in what, how tight a radius can the airplane turn? Okay, as just an example, if we were to plot power versus speed, we might be interested in both the power required by the airplane in order to maintain level flight, as well as the power available from the propulsion system. And by comparing those two, for example, where the curves intersect, we might be able to figure out the maximum speed the airplane could fly. If you look at the speed where there's the maximum distance between available and required power, you can determine the maximum rate of climb of the airplane. So lots of information comes from these plots. From our point of view, we want to understand what makes the plots look like they do so that we can make good choices in our aircraft design. Finally, we come to design. Design is a word that gets used a lot. There's a school of design at the University of Pennsylvania. Also, many engineers say they like to design things, by which they often mean they like to go into a CAD system, make a drawing, and then actually build it. But in the aerospace business, design usually means something more technical, which is we want to make a vehicle which is quantitatively related to some requirements. How far does the vehicle have to go? How much payload does it have to carry? How fast does it have to go? And design is really the inverse of analysis. Rather than having a vehicle and determining what it can do, we have what we'd like the vehicle to be able to do, and we determine what the vehicle looks like. In preliminary design, when we specify an aircraft, we determine how much it's going to weigh, how big it's going to be. We determine some basic characteristics of the airfoils and other aerodynamic details. We determine the propulsion system. Are we going to use a jet engine or a propeller? Or are we going to use an electric-powered prop? We determine energy capacity, battery size, or fuel volume, and we determine how the aircraft is going to get on and off the ground.